NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everybody here on Lab and all of you watching at home. My name is Brian White with JPL's Office of Education and Communication. Welcome to the Von Karman Lecture Series. When I was younger, personally, I was playing Little League Baseball, and as you may know, there's a lot of downtime in baseball. And I would look up at the clouds. I would just watch them glide over, which probably explains why I wasn't very good at Little League Baseball. But what I did do was I would find shapes in them like everyone else around me. What I didn't learn about or know about was what these clouds really did to our climate, how they would affect what would happen down the road, really their effect on what was happening at that moment. What can the attributes of these wondrous feather canyons tell us about the future? And as the great scientist Joni Mitchell once said, we looked at clouds from both sides now, from up and down, and still somehow we really don't know clouds at all. Tonight we'll have 3 speakers followed by a brief discussion and some Q&A. And if you're watching at home, please feel free to ask. We'll make sure you get those questions up. Our social media team will do that. But our first speaker received his PhD at the University of Melbourne, Australia, and literally wrote the textbook when it comes to remote sensing. Professor Stevens has made major research contributions in 3 related areas: atmospheric radiative transfer, remote sensing, and the topic of cloud climate feedbacks. He has a citation count over 27,000. He is a member of the U.S. National Academy of Engineering, fellow of the Royal Society, and the co-chair of the Scientific Steering Group for the Global Energy and Water Exchanges Project of the World Climate Research Program. He is the co-director of the Center for Climate Sciences. Please welcome Dr. Graeme Stevens.
Very good. Okay, I'm on, yeah. Well, thank you all for coming this evening and to give us an opportunity to talk about one of my favorite topics, clouds. No doubt you've all heard the phrase Earth is a blue planet, right? But something that's a common kind of way of describing Earth. But as we look at Earth from the perspective of the moon, we notice that, of course, Earth is also wrapped in a thin veil of white water. It's not only is it blue water that covers 70% of the Earth's surface in the oceans, but about the same area of the Earth is covered by this thin veil of white. And this combination of this veil of white water in the form of clouds, together with the combination of snow and ice at the Earth's surface, you truly would be forgiven to think of Earth as a white planet just as much as a blue planet. And it's the whiteness of the planet Earth, in many respects, that's really quite important for understanding the role of clouds in climate. And we're going to get into this topic a little bit more in a minute. Okay, so let's think about water on Earth, and you'll be shocked, I think, as to how thin this veil of water is in the sky in the form of clouds, but yet how important it is for life on Earth. Okay, so about 90% of all the water on Earth is in the oceans. It's saline and it's basically contained in the oceans. About 2.5–3% of the water on Earth is fresh, the water that we rely on to sort of support life as we know it. About 1%, roughly 1%ish of the fresh water is in the atmosphere. So it's 1% of 2% or thereabouts. About 1% of that 1% is the water in these clouds that control and influence climate, as we're going to learn. So it's tiny. Now, the water in the atmosphere is about 1 inch deep. It's barely a puddle. If you wrapped all the water around Earth from the sky, it's about 1 inch deep. And the water in clouds is even tinier than that. And the water that comes as rain is even smaller than that. So the water in the atmosphere is a tiny, tiny fraction of what's on the planet as a whole. But as you'll see, it has such a disproportionate influence on our climate. And trying to understand and predict the movement of these tiny slivers of water in the sky is really one of the great challenges in understanding climate change. So just another way of thinking about this, if you took all the water in the oceans and wrapped it around Earth in a uniform layer, it'd form a layer about nearly 3 kilometres deep compared to the 1 inch of water that wraps around in the sky. So this kind of gives you a kind of a perspective. Another interesting fact about the water in the sky, water in the planet, and as it relates to the atmosphere, if we took all the water in the oceans and allowed it to evaporate at the rate it is today without water coming back in the oceans as runoff or rain in, it would take about 3,500 years or thereabouts to remove all the water out of the oceans. Now, in the atmosphere, this tiny 1 inch of water in the atmosphere, it gets rained out. Basically, it rains about 3 millimetres a day. It gets rained out in about 10 days. So water in the atmosphere is cycling rapidly. Water in the oceans is very sluggish. It's sort of moving around in a very long time scales. Both of these forms of water fundamentally make Earth and make our climate as we understand it today. They're both so fundamentally important to understanding our climate. So we're going to focus on this, this form of water in the sky in the form of clouds and why it's important in our climate. So one question you might ask is, what would Earth be like without clouds, right? Well, it's a simple answer. We wouldn't be here to answer it, because these are the vessels by which fresh water is delivered and the fresh water that we rely on to live are delivered. So Earth wouldn't have the climate it has, we wouldn't have the fresh water and to support life has without clouds. Okay, so clouds are important, and we're going to, the next couple of talks, we'll touch on these important aspects. Clouds are important because they're basically a central role of the hydrological cycle of Earth. They deliver the rains and the fresh water to the surface of the Earth. So they're really the key part of bringing water back down from the sky back to the surface. Okay? They basically have very major radiative impacts. They're white on the one hand, but they're black on another hand. And I'll explain a little bit of that. So they both have a long wave effect, blackness in the infrared, and the short wave effect, white in the solar. And these two factors really shape the role clouds play in climate. And Kate's going to talk a lot more about this and the role clouds play in climate than these two aspects of clouds. And then the other key part is, of course, they are a key aspect of as water gets transformed through different phases inside clouds. It's a source of major heating driving the major storm systems of our planet, which in turn deliver the precipitation. So they play a kind of a critical role. And Brian's going to talk about the different ways we've been able to see these clouds from space in a very global context. So together we sort of have the topic covered, I hope, for your point of view. Okay. One way you can think about measuring the whiteness of the planet is in the context of this quantity we call the albedo. It's basically how much sunlight gets reflected, how much incoming sunlight gets reflected back to space. And it's about 30% of the incoming sunlight of the entire Earth gets reflected back to space. So Earth's albedo is about 0.3. There are some really interesting puzzles about this albedo that we as scientists haven't quite figured out the full answers to, which makes science really kind of exciting. And basically, expressed in terms of energy, about 340 watts of energy in the mean sense come into the planet from the sun, averaged around the Earth, and about 100 watts per metre squared averaged around the Earth get reflected back. And so this albedo can be also expressed in terms of this energy in watts per metre squared. So, and what we know from our measurements that we've made over time is that basically a large fraction of this 100 watts comes from reflections in sunlight being bounced back from the atmosphere, from clouds. And another part of it's from the surface. So most comes from reflection by the atmosphere and clouds, as I've already said. Right? Here's sort of the puzzle. If you look at the northern hemisphere and southern hemisphere, it turns out that the hemispheres, both hemispheres, reflect identically the same amount of energy. We can't tell the difference from our measurements, as there's no difference in terms of the amount of sunlight coming from the different hemispheres. Yet, oops, the pointer's gone. Yet the southern hemisphere, whereas we turn out, is much cloudier than the northern hemisphere. The northern hemisphere has much more land mass and snow cover and so forth. And Mother Nature acts that these two factors entirely cancel and giving us an albedo that's the same. Now, we don't quite understand whether the significance of this, but what we do understand and what we see is that clouds are the main way Earth regulates energy going out to space. Okay, so this is just an illustration to give you a sense for the sensitivity of the Earth system to changing in the whiteness of the planet. And basically, there's two panels. One panel represents different simulations from one of our advanced Earth system models of the warming of the 20th century. That's on the left as you see it. And the second is the changes of the reflected sunlight in watts per metre squared on the right that's given rise to this, that can be traced to this 20th century warming. And the differences between these simulations is just how you turn rain on and off in the clouds. It's just a certain knob that models have to turn rain on and off. And what you see is it's very sensitive. The warming itself is very sensitive to the details of the clouds and the way rain develops. That in turn can have quite a marked effect on on how much sunlight is reflected. This sunlight reflected from the planet is influenced by volcanoes. These letters there are basically different volcanoes, which have a kind of a very convoluted influence back on the clouds. But bottom line is about a 2 watt per metre squared, 2% change in sunlight reflected. You can go from a state of warming of the planet to a planet that hasn't warmed in the 20th century, just with a 2 watt change. So this gives you a sense of how sensitive the whiteness of the planet's warming is to the whiteness, so to speak. Okay, well, we've had a decade of progress, had much more than a decade of progress, and Brian's going to talk about, going back from the early days of satellites all the way through. But we've had a decade of progress where we've had some quite unique measurements about clouds that have come from active instruments, lasers and radars, that allowed us to sort of kind of like do a CAT scan through the atmosphere and look at things working inside the atmosphere in terms of clouds. And this is called the A train. And it arrived with a big bang. They wouldn't let me show this image, but basically the poster of the A train is at Caltech. It happens to be in a scene from the Big Bang. So there's a scene of Big Bang, and there's our poster of the A train right there in Big Bang. They wouldn't let us show this because I guess it's not kosher to show it. Anyway, so we've had these measurements in the last 10 years, and this has told us a lot about these tiny slivers of water in the sky that we think is so important to controlling our climate system. So here, for example, we've determined, for example, from these measurements, how often it rains and snows around Earth. We didn't know this until these measurements. We know how frequently it rains and snows, and this is a kind of a diagram here that shows you kind of distribution of how frequently it rains and snows, and you can see the higher latitudes it's kind of a dreary place. It's always raining and snowing there. If you lived in London, it's always raining in London. So, but this rain formation, and we can even see, I'm not going to talk about that, but we can even see rain forming in these clouds from space. This is quite amazing. So this allows us to begin to answer some really big questions. One big question I'm going to close with in a minute. The second thing is we now know how much water and ice is suspended in the sky. So this shows a profile of height and latitude from the equator in the middle to the polar regions either side, left and right. And so you can see clouds in the tropics, water's lofted high in the clouds up to 15, 16 kilometres, and you can see the major cloud and storm regions. So we now know how much ice is suspended, how high it's suspended. And this is really important because, whoops, I won't go back, but this is really important because the height at which the water sits in the atmosphere dictates the ability to act as a greenhouse factor and act like a thermal blanket, right? And the amount of water in the clouds themselves dictate how white they are. So you've got these two things, how high they are and how wet they are, controlling the whiteness and the blackness of the clouds, so to speak, where the blackness is a greenhouse effect. Okay, so this is a big question. How are the clouds and the hydrological cycle changing? This is kind of a really big question that sort of motivates our science as we go forward. And it's posed in a slightly different and a simple way by a UK minister to the chief scientists of the UK Meteorological Office. After a major flooding event happened in the UK, this minister asked the chief scientist a very simple question. How bad are the rains going to be in the future? Are we going to expect more of this kind of flooding? Now, we have some sort of broad understanding of why we think the rains will become more intense in a warming world. But there's much more to it than just these simple thermodynamic controls on the cloud systems that sort of suggest that these rains will become more intense. So we can't give really definitive answers. We can give suggestive answers to this kind of important question, but we can't yet give definitive answers. But our science is really progressing, and I expect that by the time I retire, we'll be able to give some much more definitive answers with the modelling systems that we have. So let me just close. Summary comments. We've made significant progress in a number of areas in terms of trying to understand this sliver of water wrapped around Earth. How much, we kind of can quantify now how much water is suspended in air. Very difficult. That was, you can see why it's such a challenge, because it's such a tiny amount of water, but it has such a big effect. We sort of understand how it rises and how now it falls to the surface, so that we can understand it as part of the cycle in a quantitative way. And the influence of this tiny amount of water on the Earth's energy balance and just how wide Earth is and why it matters, we kind of much more quantitative understanding of this. But there are big challenges that remain, like the UK Minister's simple question that still runs deep and influences our thinking in terms of our science. So that's my spiel for the 12 minutes. And I guess I move off, right?
Thank you. Thank you, Dr. Stevens. Our next speaker, Dr. Brian Kahn, got his master's and PhD in atmospheric sciences at UCLA. He is currently a research scientist working closely with the Atmospheric Infrared Sounder, or AIRS group. His research includes active and passive remote sensing of clouds, temperature, and water vapor, with a specific focus on observing cloud and climate-related atmospheric processes, leveraging the natural synergy of satellite sensor constellations. Welcome to the stage, Dr. Brian Kahn.
Well, thanks very much for coming to the von Karman lecture. So I'll start with something slightly different, if I could switch forward here. I know we all love moon landings. The moon landings were incredible, a great human achievement, and the future moon landings to come. But I think this was an equally important moment in NASA's and human history, frankly. In April 1960, 59 years ago to this month, we finally launched a satellite into space where we looked back down at Earth, and we got a picture of the planet and the clouds in the atmosphere. And what you see here are the first light images from the TIROS-1 satellite. You can see we're over the Middle East in this general region here, and you could see the movement in the images to the west. So these were the first light images of our planet from a polar orbiting satellite. So I think it's a great moment. We've come a long way in these 59 years, however. We have much more advanced instrument calibration and engineering methodologies, and technology has advanced rapidly in this time. We have a much greater ability now to cover the entire Earth constantly within a matter of minutes with satellite images. There's advancements in the data storage, how we downlink data from the satellite to the ground. These are not trivial issues. How we process these data and software. And also, the other thing that we probably don't appreciate very much, and as Graeme alluded to, we have knowledge not only of where the clouds are, but what they're made of, whether they're ice or liquid. And there are scientific advancements in how we actually obtain these cloud properties. So I want to acknowledge that. Okay, so this is the state of the art. This is the advanced baseline imager. And what you see here are 16 channels. And this is from a geostationary imager that's high enough above the surface of Earth that it actually rotates with Earth. And it's at the same rotation rate. So it looks at the same place on Earth all the time. And this is just a small little region over the United States. And these are 16 different channels. you'll see visible and near infrared, sort of the whiteness that Graeme alluded to in the upper 4 or 5 channels. And then the blackness, the infrared or the emission, is in these different channels here down low. You could see storms and movement of clouds through the United States. There are much more detailed images than this available as well. So having just such a level of detail now available to us is revolutionizing how we think about clouds. So I thought this was an appropriate image since we're in the von Karman Auditorium, which you actually see here in the Southern California bight right off the coast, are these little von Karman vortices. And these indicate wind flow past the Channel Islands. So you'll see some of the islands right here. And as the wind flows past the islands, they create these little circulations in the lee of the island. So when you look at a satellite image, it's not just the image or the whiteness that's important. That's just the visible part of a larger process, a complex process happening in the atmosphere, where you have temperature, water vapor, wind is flowing, and the clouds are just sort of the visible part of it that you see. There's much more to clouds than meets the eye. So the key is that we need to observe these things at the same time and place. So another exciting recent development is this ABI instrument is actually coupled with a geostationary lightning mapper. And what you see here is a visible data. So this is the whiteness of clouds, the reflected solar radiation, and then lightning detection is actually mapped within the clouds. So this is really cool. So you'll see thunderstorms just going like crazy in the central US, but only certain parts of the clouds are really active, okay? So the lesson here is just because you see a big bright cloud doesn't mean that there's a violent thunderstorm everywhere in that cloud. So these types of observations are giving us more insight as to how these storms work and how things are structured. So those are geostationary satellites, and Graeme talked about the A-Train. So the A-Train is our most state-of-the-art polar orbiting satellite constellation that we have to date. And geostationary satellites are really great tools for weather forecasting, for severe weather warnings, for commerce. There's a lot of applications that geostationary data is very important for. But these satellites, they're still not quite accurate enough to monitor climate change. At least that's sort of the current thinking. Also, another problem is that geostationary satellites do not observe polar regions. So since they're sitting above the equator staring at the same place all the time, they actually don't observe the poles where climate is changing most rapidly, okay? So polar orbiting satellites will fill in these regions, and this is sort of where our state-of-the-art instrumentation is located in these particular instruments. So I'm just showing you an example of my own personal research here, getting at it's not just whether there's a cloud or not, but it's the characteristics of the clouds that really matter for understanding how the atmosphere works. So this is ice cloud frequency over a 14-year period. You could see the time at the top, and these are monthly averages of the entire globe. And you could see that ice clouds kind of move around with the seasons. So the seasonal cycle, it kind of waves up and down. Paradoxically, there are much more ice clouds in the hot tropics. So maybe a lot of you don't know that. It's pretty interesting. But watch the clouds move a little bit east here in the Central Pacific. That was actually an El Nino that occurred in 2016. You might have remembered the strong El Nino that we had where it didn't rain in Southern California. Okay, so the next loop that I want to show you here is not the ice cloud, but it's all clouds. You could immediately see the pattern is different. So the ice clouds tend to occur in the tropics, but the liquid clouds tend to occur in maybe middle and higher latitudes. And they have different seasonal cycles associated with them. So that's really kind of like the bottom line message here is there are different types of cloud properties that matter with these issues that have been discussed by Graeme and will be discussed by Kate as well. So I just want to end on some summary research results that I think are very interesting. In the upper left is a 25-year record of satellite data that shows where clouds are increasing, which is in green, and where clouds are decreasing, which is in red, over the last 25 years. So you could see some areas of the Earth are getting cloudier, some places are getting clearer, okay? The climate models, which Kate will get into, show similar patterns, like this region here where clouds are increasing seems to be pretty similar to the observations. But there are other areas that disagree. So you can make a plot of where they agree and where clouds are increasing, both in the observations and models, and those are the green areas down here. And then where clouds are decreasing, both in the observations and models, those are the red areas. So we're definitely starting to peel apart the behavior of the atmosphere in a little bit more of a fine-tooth comb detail than we were capable in the past. Yeah, I think that's about it. Thanks.
Thank you, Brian. You always got to trust a person named Brian. Now, our final speaker and special guest comes to us from the East Coast. Dr. Kate Marvel is an associate research scientist at the NASA Goddard Institute for Space Studies and at Columbia University, where she uses supercomputers, big data, and satellite observations to study climate change. Before becoming a climate scientist, Kate received a PhD in theoretical particle physics from Cambridge University. She has given a TED Talk, appeared on Meet the Press, NPR's Weekend Edition, and Star Talk. She writes the Hot Planet column for Scientific American, has written for Nautilus magazine and the On Being Project. She's got some game, folks. Please welcome Dr. Kate Marvel.
So I work on climate models because I'm really interested in the future and nobody has invented a time machine yet. So that's one of, I know, get on it, NASA. So this is one of the only ways that we can actually see the future. And fortunately, we have some confidence in the ability of climate models to tell us something useful. Because if you look at how they act over the recent history, they're able to reproduce the warming trend that we've seen fairly well. But when you look forward into the future, it's a different story. So these are different climate models that are all run subject to the exact same scenario. And I want to be clear, all of them are warming because carbon dioxide is a greenhouse gas and it warms the planet. But some of them are warming only about 2 or 3 degrees Celsius. And some are warming 4, 5, 6 degrees by the end of the century. And I want to put that into context for you. 4.5 degrees is the difference between now and the last ice age. So this is something that is kind of embarrassing for climate scientists, that we know it's going to get hot, but we don't know exactly how hot it's going to get. And you know, like we had one job, right? But one of the reasons, the main reason I think that we don't know how hot it's going to get is because we don't know what people are going to do. We don't know what emissions are going to look like by the end of the century. Are we going to cut emissions or is it going to be business as usual? But even if we remove that uncertainty of human behavior, there's still uncertainties in the climate system, physical things about the way the planet works. That means that we're not 100% sure exactly what the climate's going to do. And so in order to remove that uncertainty associated with human behavior, we define a metric which is artificial, exists only in climate models, but is extremely useful. And we call that equilibrium climate sensitivity. So what we do is we abruptly double atmospheric carbon dioxide. In a model, we're trying to do that in the real world. Let's not do that. And then we wait for the climate to come into equilibrium. And this is a process that takes hundreds or thousands of years. And after the climate comes into equilibrium, we see how hot it got. We measure the global average temperature change. So this is something that's really simple. You can do this in any climate model. But if you look at what different climate models do in response to this simple experiment, you see a wide variation. So our best estimate right now of this value of climate sensitivity, how warm it gets when you double atmospheric carbon dioxide, is somewhere between 1.5 degrees and 4.5 degrees Celsius. And that's a really big range right there. So why aren't we 100% sure how hot it's going to get? Well, that's because temperature changes cause changes to the climate, changes to things we care about, like rainfall patterns and clouds. And those climate changes can then themselves speed up or slow down the warming. They feed back onto those temperature changes. So for me personally, the most intuitive feedback is, Graeme mentioned albedo. The most intuitive feedback is what is going to happen to the albedo of the planet as it warms up. Right now, the poles are covered in ice. And when you make it hot, ice melts. So that ice, which used to do a pretty good job of reflecting sunlight back to space, is now gone and reveals darker ocean or land below. And that is a lot less good at reflecting sunlight back to space than ice. So this is what scientists call, and this is the worst terminology scientists have ever come up with, a positive feedback. Because when normal people hear positive feedback, they think, I'm doing a great job. And when scientists say positive feedback, we mean something that is going to destabilize the planet and make climate change even worse. So another example of a positive feedback, AKA vicious cycle, trying to get scientists to adopt this new terminology, is water vapor. So water vapor itself is a very powerful greenhouse gas. And warm air holds more water vapor. So if you warm up the atmosphere by, for example, putting carbon dioxide in it, that warm air will hold more water vapor, itself a very powerful greenhouse gas. So this is an example of another positive feedback. But these ice albedo and water vapor are fairly well understood. This is not what's responsible for that spread in model predictions. The thing that's largely responsible for the spread is clouds. So in large part, we don't understand what climate is going to do. We don't understand exactly how hot it's going to get because we don't know what clouds are going to do. And that's because clouds play kind of a dual role in regulating the climate, as Graeme talked about. So these here, these clouds, preferentially low, thick clouds, these are doing a really good job at blocking sunlight. So if you are living underneath one of those cloud decks, you are having a pretty gloomy day right now. And we know that these low, thick clouds are extremely effective at cooling the planet because they block sun that would otherwise reach the planet's surface. So low clouds block the sun, and they make it colder. But clouds also do something else. As Graeme talked about, clouds have a really powerful kind of blanket effect. Clouds themselves have a powerful greenhouse effect, which you can see in this slide taken in the infrared. And these are mostly those high clouds. They trap thermal energy from the Earth's surface, and they make it warmer. So clouds are really confusing for many reasons, but primarily because they play this dual role in the climate system. They make it hotter, but they also make it colder. And that's one of the reasons that they're really hard to understand how they're going to go forward into the future. So one idea is to turn to recent history to try to get some clues about the future, because we've emitted carbon dioxide, and it's gotten warmer. So maybe we can take observations of the global temperature change and the carbon dioxide that we've emitted so far and use that to try to estimate this value of climate sensitivity, how hot it's eventually going to get. So when you do that, your best guess is about a little bit less than 2 degrees Celsius, which is bad, don't get me wrong, but it's not necessarily catastrophic. However, the equilibrium climate sensitivity, the best guess estimate that you would get from climate models participating in an intercomparison project called CMIP5, is more than a degree hotter than this, 3.1 degrees Celsius. And so this begs the question, are the models running hot? Are these models overly sensitive? And this is something that I really want to be true, because I really don't want climate change to be bad. But unfortunately, we have to be very, very careful when we are making inferences about what is to come from what we've experienced so far. The past is very different from the future. So this is a slide of what actually happened. This is the warming pattern that we have actually experienced in recent decades. And I've subtracted off the global average temperature increase, because otherwise you would just see a sea of red here to really bring out the pattern here. And you can see that this has been characterized by anomalously cool temperatures right here in the equatorial Pacific. And those anomalously cool temperatures have been really good at spurring cloud formation, in particular low marine stratocumulus clouds. So in recent decades, we've actually seen an increase in clouds in these marine stratocumulus regions. And these are those low, thick clouds that are very effective at cooling the planet, at turning away sunlight that we would otherwise get. But we just happen to have experienced one iteration of reality. Climate change is occurring on top of a background of natural climate variability, weather, El Nino, La Nina, natural climate oscillations. And right now, the signature of that carbon dioxide is not strong enough to overwhelm that natural variability completely. So we happen to have experienced one iteration of climate variability, but it could have been otherwise. And we can use climate models to explore different counterfactual scenarios. What warming patterns and what cloud patterns could we have experienced had we just happened to have experienced different weather, just by sheer randomness? And all of these patterns, in turn, look very different than what we think is to come. So when we're talking about the climate in equilibrium, we're talking about a planet that's had a long time to adjust to what's been done with this. In particular, regions that are really, really slow to warm. For example, the Southern Ocean down here. Those regions will eventually warm up. And this is not a pattern that we think is achievable by random internal variability. This is not a warming pattern that we have seen before. So what the climate models are telling us is that we are moving into a future with a warming pattern and subsequent cloud cover that's perhaps different than anything we have ever experienced before. So that long-term warming pattern, that possible new normal, is what the models are using when they are telling us this future distribution. So that best guess of 3 degrees climate sensitivity, that comes from that warming pattern in the far future. What we could have experienced, this purple distribution, is what happens when you run climate models with the present day greenhouse gas emissions, but you don't allow them to evolve forward into equilibrium. And you'll note the fact that right now we are experiencing a disturbed climate that's really very far out of equilibrium means that the climate models say, no, you actually should infer a climate sensitivity that's less than what you'll get in the future. And the mode of variability that we just happened to have experienced, we just happen to have gotten lucky. And that gives us an estimate of climate sensitivity that's even lower still and commensurate with the observations. So I want to back up and end with some conclusions. So the first is the reason I don't get invited to parties anymore, which is that I think it's probably going to get worse. As time goes on, almost all the climate models project higher climate sensitivities. Climate models project that clouds will rearrange themselves and change in ways that will make the warming worse. And moreover, we happen to have gotten really lucky. In the real world, we just so happen to have experienced a pattern of natural variability that led to a period of cool temperatures, particularly in the equatorial Pacific. And we know why this led us to infer low values of climate sensitivity, because this warming pattern sparked low cloud formation, which blocked sunlight and slowed down the warming. And I think the real takeaway from this is that the past is not the future. And we have to be very, very careful when we make projections from the future by just extrapolating forward to the past. Because we may be moving toward a future where warming patterns, and particularly cloud cover, are such that we've never experienced them before. We may be moving into a future for which there is no analog. So thank you very much.
Thank you very much, Kate. Before we head into our discussion, I would like to let you all know that you can also become a citizen scientist. Pretty much everybody's got a phone or a laptop or some sort of mobile device now. But if you go there, particularly with clouds, we have the Globe Observer app. It's actually a NASA app. You can go on there and download, and you can help us see what's happening around the skies, where you are. You can take a picture of it, and you would become a citizen scientist. It's all the hard work is really done for you, so I urge you to go find that on your website or on your app or whatever you got. Now, you're all magically sitting down. It's magic. It's TV magic. So one of the more fascinating topics for me, and this is what I've enjoyed about putting this all together, is I guess the science aspect of it, in the fact that there was a time yesterday when we were all talking about this that you all disagreed with each other. And I loved seeing that. And as Kate referenced, the models are tough to match up, and one of the reasons is the feedback, the poorly named positive feedback and negative feedback. And I hope right now online we're only getting our kind of positive feedback. Is there feedback, both negative and positive, that we're still discovering or that could drastically change the models easily, like today?
Me first?
You go first. No. This is where we disagree a little bit. That's good. That's good.
So we know a lot about clouds, but there's still a lot that we have yet to understand. So as Brian showed, we have evidence that clouds are changing in a lot of the ways that models say they should. We have evidence that high clouds, those sort of blanket clouds that are so good at trapping radiation from the Earth's surface, we have evidence that those are probably moving higher, which actually increases their thermal blanket power. So that is an example of a positive feedback or vicious cycle. We have some evidence that those low, thick clouds in the tropics are being pushed toward the poles by changes in the circulation. And that is also positive feedback, because if you're really good at blocking sunlight, you probably want to live in the tropics where the sunlight is the most intense. And if you move toward the poles, you're probably going to be less effective just because you're blocking weaker sunlight. There is an example of a negative feedback, which is, as Brian mentioned, the composition of clouds. We expect some of those ice clouds, or what we call mixed phase clouds, to become kind of juicier as the ice melts in a warmer world. That's an example of a negative feedback, because those juicier clouds will actually become better at blocking sunlight. This is something that's already incorporated in climate models. And unfortunately, there may be evidence that we, at least in the last generation of models, overestimated that impact. So that may be less mitigating than perhaps we would have thought about. But I guess my take-home point is that it is hard for me to think of clouds constituting a significant negative feedback. And in plain English, that means I don't think clouds are going to save us from global warming.
Yeah, in some ways I kind of agree with Kate that we can't hope that clouds are going to save us, because I don't know we can think that way. But there are pathways where which negative feedbacks can occur, and we don't really fully understand all the interactions that take place in the Earth's climate system and how the role clouds play. So for example, just as a simple observation, we know that for those regions where those big high clouds are, the big thermal blanket clouds are in the tropics, that those ice clouds that Brian shows you moving back and forth, but they're in the tropical latitudes. Well, over multi-annual timescales, the tropical atmosphere breathes. It goes up and it goes down, goes up and it goes down. And as it breathes, the high clouds go up and goes down, just like Kate said. But they also get thicker and wider. And that's a negative feedback, you see. So aspects of those clouds and how it ties to the breathing of the atmosphere, we don't fully understand. There is a pathway by which a negative feedback could kick in, but it won't be, I can't see it overriding the effect of the continuous build-up of greenhouse gases. It could mitigate in certain areas, but we can't. The feedbacks we know of that we're somewhat confident about all seem to be positive, but it does not rule out that there are negative feedbacks in the Earth system, just like I said, right? So that's where I come from. I'm sort of more open-minded to suggest that there are negative pathways, but I just don't know that they're going to be strong enough to save us.
Yeah, I'd just like to follow on to something that Kate said at the end of her talk about the pattern. The pattern really matters. whether you have more warm water in the future in one side of the Pacific versus the other is really key to telling you whether there's going to be more low cloud, maybe a negative feedback versus a positive feedback. So we really don't know what's going to happen in the future. Also, despite all those wonderful observations that we have now, we really can't see within deeper precipitating clouds very well. So we don't know how fast the air is rising. We don't know whether it's a slow, large-scale movement or small, little violent movements, and how that actually maps onto creating cloud structures. So there is plenty for us to do in the future.
I'm sorry, I know you wanted to fight, and we all kind of...
No, you guys are great. Just fine. I like that you all get along. It's very nice. Brian, you had that great image of the storms rolling across the... I really enjoyed that. It was very cool to look at, but what is one of those links between clouds and storms? What does feedback affect the future of these storms? Does it make them more severe? Please.
Yeah, no, that's a great question, Brian. I don't know, the way that I view it is how Kate and Graeme discussed it in two different pieces. You have a hydrological cycle aspect, so that's how fast water moves around, evaporated, forms precipitation and comes back down. So that's about a time scale of 9 to 10 days or so for a given molecule. And then there's the radiative consequences. So the cloud distributions as a whole control the climate sensitivity to some degree. And then there seems to be an inverse relationship between the strength of the climate sensitivity and the strength of the hydrological cycle. It appears that some models that have a lower climate sensitivity actually have a stronger hydrological cycle increase, which implies an intensification of storms. But it's definitely like an area that we're thinking hard about right now, and we don't have firm answers on this.
So there's a very simple reason why we think storms will get more intense. And one of the most really undeniable feedbacks in the Earth system, as Kate mentioned, was this water vapor feedback. As the air gets warmer, all things being equal, it'll hold more water in the form of vapor. The more water in a volume of air that condenses, the more latent heat is released. The more latent heat is released, the more violent are the storms, because that's the dynamical heat. That's the forcing function of the storms, is this latent heating. So we think, all things being equal, that greater condensation will lead to more intense, vigorous storms, which means probably heavier rain. But I said all things being equal. And one of the key things we don't yet resolve in models, they do a great job, but the major convective storms that give us the Midwest storms and tornadoes and those sorts of things, those major storms are really poorly resolved right now in climate models. So while we think there's an overriding basic physical process by which storms would get more intense, the models don't quite resolve them faithfully enough for us to be 100% sure. But that's going to change. In the next 10 years, we're going to see models that actually resolve individual thunderstorms. We actually see them now. They're not quite climate models, but that's the evolution. So I think it's going to be an exciting time, because we can be able to say something quite quantitative about storms and how storms will change in a warming world. And that's kind of a big issue for society.
Okay. Anything to add, Kate?
Nope, you said what I was going to say.
Great. You guys are so agreeable.
We'll argue tomorrow.
We're going to open it up for questions. If anybody in the audience has a question, there's a microphone right there in the middle. Go ahead and line up. While you're working your way over there, we're going to ask some of the online questions. And this one really kind of has to do with what we just heard. Nintenzome on YouTube asks, will this contribute to climate shift research?
You can take that one.
I think so. I mean, I have an embarrassing admission, which is that I actually do not care that much about clouds. I came to cloud research because I care about how hot it's going to get. And clouds are such a vital part of the climate system. Clouds are so important in understanding and determining basically how hot it's going to get, and then all of the consequences that flow from that. So if we could really sort of determine and learn more about cloud behavior, we could be a lot more precise with our predictions for the future.
So she really does care about clouds. Right?
Great. Yes, right there in the front.
Hello. My question actually is for Brian. And you earlier had put in, or not put in, that doesn't make sense. You earlier in your speech had done a great job of showing your evidence. And one of your slides had what was called ECF.
Oh, yeah.
Can you please explain what ECF is?
Sorry.
That's okay.
That's something, it's called an effective cloud fraction. So
Okay.
I should have changed the title to something more simple. Yeah, it's basically just tells you how much cloud there is.
The area of
It's
cloudiness.
kind of the area, and also like how thick the clouds are, but multiplied together. So it's not
effective cloud fraction.
Yeah, it's not just a coverage, but it also accounts for how kind of opaque or transparent the clouds are to radiation.
It's like a volume.
Great.
Like a volume, yeah.
While he's finishing taking that note, we'll ask another question from online. How do geostationary satellites exist in the hot thermosphere? Dean on YouTube wants to know that.
So geostationary satellites in the hot thermosphere, so they're way above it. They're at about 36,000 kilometers or so.
They're way out
Yeah.
there. I mean, way out there. There's 6 radii out there. They're
Yeah.
so far out there.
There you go, Dean. They're so far up there.
But
Next
that-
question.
But they have to be able that way out there so that they can basically wrap around, move with the Earth, and allows them to stare. The unique thing about geostationary, they allow us to stare at Earth and see things changing, where the polar orbiting satellites are going whizzing over. In 90 minutes, they're wrapped around Earth. So geostationary is very valuable, and the geostationary satellites, interestingly enough, are getting more and more capable. Before they were just like cameras. Now they're getting to be really serious kinds of measurement tools that we can now see from 36,000 kilometres. They're even talking here at JPL about putting radars up on geostationary, 36,000 kilometres with an antenna so big it's going to block the sun, and that'll cool the Earth. Yeah. So, geoengineering we call that. Right.
I did have one last question, and that was for Kate, which is earlier you had given CO2 as carbon dioxide. Is there a chemical formula for water vapor?
H2O?
Okay, that's simple. I didn't know. Okay, thank you.
It's a very special molecule too.
It's
Very special shape that allows it to radiate.
That is my favorite molecule.
right.
A very, very good set of presentations. So much focus has been on what the climate will be in 2100, and there's very few of us who are here today that's going to be here in 2100. And so I'm asking how much we can say about, say, 2050. So that's 31 years from now. And it would seem, you talked about the tendency to have more intense storms. It would seem like the storms are getting worse over just the last 10 years versus the previous 10 years. But of course, that could be variability. So I know that the things that are happening as far as melting of the ice sheets in Greenland and the Arctic Ocean and Antarctica, those processes tend to be nonlinear, and so you get, you're getting rather dramatic shifts. So the question is, I mean, this is very hard because the models are so complex, but do we think it's going to be kind of exponentially getting worse in the next 30 years, or just kind of gradually getting worse?
I mean, that's a really great question with so many layers to it, because it gets at something that I think about a lot, which is when I think about global warming, so the increase in the average temperature of the planet, my first question is, who cares? because nobody actually feels the average temperature of the planet. You know, what we feel is the impacts of that. So in California, you know, forest fires, you know, mudslides. You know, in New York, we're worried about sea level rise. And those impacts, so asking about badness, you know, is really complex because a lot of those impacts scale nicely and linearly with the temperature, and some don't. And then even when you're looking at just the global average temperature itself, there's always the possibility for tipping points. You know, so I talked a lot about known unknowns, so things that we know we don't know. There are also unknown unknowns, so things that we don't even know we don't know.
You sound like a politician.
And you know, those could be things like, you know, substantial negative cloud feedbacks, but those could also be tipping points in the climate system that kind of push us away from this sort of linear increase in temperature to a totally new regime. And so that's something to think about. That's something to worry about. But the thing about unknown unknowns is that they're hard to think about because you don't know them. So you know, I think it's a great question, and I think it's probably worth like several PhD theses worth of answer.
So let me just, one specific thing is the possibility that the permafrost will accelerate the melting. The melting of permafrost will accelerate, and it will have more methane and more CO2 released, and that would be an example of one of your known unknowns, right?
Right. So permafrost melting almost certainly, well, definitely releases methane into the atmosphere. And methane is a very, very potent greenhouse gas. Sometimes, I think periodically in the media, there is a lot of, you know, sort of a scare about, is there a methane bomb? Is it going to happen all of a sudden? And I think there's not a lot of evidence to support kind of an abrupt bomb of methane going off, but there is a lot of evidence to support that sort of slow and gradual feedback. So is it going to make things worse? Almost certainly. Is it going to dump a lot of methane into the atmosphere immediately? Probably not.
Thank you.
Thank you.
Before our next question in-house, these two from the interwebs are closely related. Wesley and Caleb, both on YouTube. One of them asked why there's so many different types of clouds, and Caleb asked, why are clouds gray?
Why are there so many different types of clouds? It's really sort of an arbitrary set of definitions that we have for cloud types. I mean, the WMO classification system, I think, is close to 200 different cloud types. From surface observers, there's typically 8 to 9 types that dominate. Sometimes you just call clouds liquid versus ice, or they may have the two phases mixed together. So it really depends on how you think about clouds and what aspect of them you want to quantify.
So I might just make a comment. Actually, the naming of the clouds has been considered to be one of the great achievements in the human endeavour. And the reason for that is it was done by a chemist. His name was Luke Howard back in 1802. And before that time, it was felt that clouds could never be categorised because they're so variable and so moving and so forth. And he was able to come up with a strategy to name them that's persisted ever since. And that naming of clouds was perceived to be a great sort of philosophical advance of the time. And it was actually what gave rise to meteorology as a science. It wasn't until the naming of clouds that we begin to realise that clouds played a role in science. They started speculating about, you know, what they're made of and so forth back in 1800. So the naming of the clouds and the cloud types has a deep-rooted influence in the history of the study of the atmosphere. So it's something that's sort of near and dear to me in some ways. The reason there aren't an infinite range of clouds. There's different cloud types that are organised by the dynamics of the atmosphere. So the stratiform, those clouds that Kate talked about, the low clouds that are highly reflective and block the sunlight, they live in a world where the air is primarily actually sinking above, and they're flat. They're stuck in the lower part of the atmosphere because the air's sinking below. So that sort of sets up one sort of cloud type. Other cloud types are where it's turbulent, and you've got land surface and mixing, and then the other cloud types are where you've got major movement of air pushing moisture in, and it goes deep convection. So it's sort of controlled by the modes in which air moves around and lifts water. And there are only a handful of modes in which ways that sort of really happens. And that's why sort of the types of clouds are, there are 8 broad categories, but there are subcategories of those, you see. So, so the naming of clouds was, as I said again, was perceived to be one of the great endeavours of human philosophy at the time, where we named something that they thought could never be named. Only God could name clouds because he had control and humans could not understand. But Luke Howard came forward, and he wasn't even an atmospheric scientist. He was a chemist. That was quite amazing. Anyway, that's a little side of history. Sorry,
great
I
answer.
waxed.
We've got time for one more question. Our gentleman standing right there in the middle.
Is it possible to ask a pair of questions?
Sure.
Sure, you can ask questions and follow up.
I'm
Here's what I will also say is that our speakers will stick around for a couple minutes afterwards. So if you have questions, you can come up and ask them that.
First one should be a quickie. In the embedded lightning strikes and discharges overlaid with the clouds, do those function as a proxy for how much vertical lift there is in a given environment?
Yeah, so people do use lightning data as a proxy for the vertical motion. It's also an interesting proxy for what the ice particles are shaped like in the cloud too.
Yeah, usually it's typically like the mixture of water and ice.
Yeah.
Makes the charge separation. So it's a kind of a proxy for, you got air moving up that has both water and ice in it.
Cool. And a second question, what are your thoughts on efficacy, scale, and morality of using or geoengineering in the context of generating clouds? Like if you had rafts of black and white reflectors that were powered by solar energy, that you could change the albedo of regional areas in the ocean, generating low cloud types. What would be your thoughts on using nature to help undo what we screwed up?
Well, I have strong thoughts on this, but I'll let someone else say.
Well, why don't you go first? Because I also have strong thoughts.
Okay, so I'm from Australia, obviously, because of my accent, right? And we've done biogeoengineering, and we've screwed it totally up. So if you don't understand the system, you don't want to kind of engineer it. But here's a problem. There's a hypothesis that you just put stuff in the cloud and make them brighter, right? This is one of the concepts, right? The brightening of the clouds. Well, it turns out if you actually really study this carefully, which we have done, 30% of the time the clouds actually get darker when you put aerosol in. So it's not clear that just putting aerosol in a priori will brighten the clouds. So that's just an example of, if you don't understand the system fully, you better not tinker with it, because you can actually get a response that's actually quite different than you expect.
Yeah, I would just say, even if it did work, even if you did manage to lower the global average temperature, there's so much that accompanies that. So, that doesn't, if we don't cut emissions at the same time, that doesn't do anything about ocean acidification. We still would probably see disruptions to rainfall patterns, because, blocking sunlight is not a perfect mirror image of the greenhouse effect. And I totally agree. There's so much about the climate system that we do understand, but there is so much that we don't understand. And you can make an argument that we are actually geoengineering the planet right now, inadvertently. But I don't think that for me is a compelling argument to then turn around and do this deliberately.
Kate made the point that we still have uncertainties about clouds and the climate models, right? So why would you run a climate model and geoengineer clouds in a climate model when there's such big uncertainty on them, and try to convince anyone that that's the way you're going to bring the planet back? There's no logic to it, really. You've got to have the right tools to be convincing. And right now, I don't think our tools are precise enough to, guide us, as it were.
Great.
Cool. Thank you.
We actually do have one more question, actually.
So my question is just related to the variable of frequency, and I'm curious because from some of the stuff that I've read about, in my opinion, frequency technologies would be one of the most dangerous threats to mankind, or I guess it could be the most helpful too. So I'm wondering if we look at that in things like HARP technology, and some of the things just myself as a regular civilian notices in the sky, such as, people talk about contrails and chemtrails. I know there's a difference, like contrails aren't gonna last very long. Chemtrails seem like they would last longer in the sky, and I see patterns that I never studied in a science class related to cloud imagery when I look up in the sky. So there's definitely something going on, and I'm wondering if I don't know what kind of security access the three of you have, but what could you enlighten this audience tonight with that information?
Hey, Brian?
I'll take that one.
Sure, why not?
Yeah, so I think you're referring to these somewhat linear trails that you see in the atmosphere, usually associated with cirrus clouds, right?
You tell us, yeah.
Yeah, so those are called condensation trails. So they occur from the seeding of aircraft emissions in a supersaturated environment with respect to relative humidity. So as this stuff is seeded in the upper troposphere, it actually condenses what available moisture is around there into these tiny little ice particles. And they're very dense. So you see a very thick stream of this coming from the back of the airplane. Now, sometimes, if the relative humidity is high enough, these will last for a while. Like you'll see a long contrail.
Well, I understand contrails, but I can look in academic databases and I can see evidence that weather modification is something that's part of our history, but it's not something that is acknowledged on a mainstream level. So, I'm talking about the HARP technology, it's there. I'm talking about weather commodities,
I would just say
those are there.
Well, Brian was answering your question that you were
Well,
talking.
contrails though, but I'm talking about specifically what would appear to be chemtrails if they're lasting longer than just a momentary thing, which a contrail would do.
They can last, and then sometimes they're not only just linear, but they'll spread out. They'll
and
spread
then
out.
Also the X hatches that we're seeing, what is all that about? It's this very distinct
Well, that's
pattern.
because you have planes flying underneath each other, orthogonal to each other, and
Another thing
you'll
that
get
I've
a hatch
heard
pattern.
is-
Well, that's actually all the time that we do have. If you want to keep asking, we can
I'm
ask
just
more
wondering
as we
'cause
come up.
I'm also aware that the aerosols can prevent lift in the atmosphere. So I have a lot of questions. So
No, that's great, and we've
I
got
should
plenty of
become a
time to stick
scientist.
around and answer for it, but we're actually just out of time. We're actually a little over on time. So thank you all for your questions. I do want to thank Dr. Graeme Stevens. Big round of applause. Dr. Brian Kahn, another round of applause. And Dr. Kate Marvel, who flew all the way out here from NASA GIS. Please join us next week when we next month when we talk about CubeSats and SmallSats. Thank you. Have a great night, everybody.